So hello again. This is the Bioelectricity course. I'm Roger Koch Barr, and this is week 3, segment 10. We were talking about channels and how channels go open and closed. Because they're just opening and closing seemingly randomly, though more frequently under some circumstances than others, we really need to think about channel openings in terms of probabilities. But first, let's just think about what we have said. It is really amazing that critical functions of humans depend on probabilities. There's not a mechanism, not a deterministic mechanism, A causes B, but rather probabilities. The channel is probably open, but then it may be closed. The channel is probably closed, but then it may be open. Of course, it'll work out in a statistical sense if there are enough channels, because we can rely on their average behavior. But it is still quite remarkable. So the issue is, how can these channels be understood quantitatively? Which turns into how can these probabilities be determined quantitatively? So I'll just make a little sketch here. We're not going to try to analyze this problem in detail right now, but let's just make a little sketch as to how we might think about it. First, we can say that in some patch, there are a total of n channels, and at a certain moment, NO are open and NC are closed. Now, the number that are open and closed is dynamic and changing randomly. We can write what is happening as an equation by saying that the number that are open is changing as a function of time, dn0 dt, the rate of change of the number that are opened, by two processes. First, there's a process where channels that are closed are reopening, and that's associated with this rate constant alpha. Then there's a process by which those that are open are going closed, and that's associated with this rate constant beta. You notice that alpha and beta somehow or other are built into the membrane. We are supposing that alpha and beta are not constants. Rather, alpha and beta change. And in particular, they change when the transmembrane voltage changes. But they're constant for a constant Vm. So let's go through that again. As long as the membrane potential is constant, alpha and beta are constant. But if the membrane voltage changes, then alpha and beta change. They change with Vm. We're not working on this problem quantitatively right now, but if you do work on it quantitatively, solve the differential equation for constant Vm, that is to say for alpha and beta constants, then the fraction of channels that are open will become alpha over alpha plus beta. So let me ask you, can you do that problem? Can you solve that differential equation and find what the actual solution is? If you do, you can see not only that ultimately the fraction becomes alpha over alpha plus beta, you can also see how long it takes for that to occur. So the crucial result here is if you framed it this way, the channels that are open will, on the average, be alpha over alpha plus beta, and alpha over alpha plus beta will be a function of Vm? Or as we saw in the channel segment, if you have a higher voltage with a potassium channel, there's a higher fraction that'll be open when the transmembrane voltage is greater. Now, how do we get specific values for alpha and alpha plus beta? We have not provided any way to do it. So the fact is, up until now, nobody has figured out how to get specific values for alpha and beta, except by measurement. So what we have is we have measurements for different kinds of tissues, and the different kinds of tissues, the measurements have been captured in equations that we can use for further analysis. But so far as I know, nobody yet knows how to find values for alpha and beta based on some underlying principle. We will discuss this further as we go forward in the course. Here's some trees in the North Carolina woods. I thought you might enjoy seeing them. Thank you for watching. We'll see you in the next segment.